So today we're going to be looking at some organic functional groups, and we're going to apply what you know about intermolecular forces to these. You do not need to memorize any of this. Mainly, I want you to get comfortable looking at these scary looking molecules and be able to just look at the structure and figure out what the polarity is based on what you already know, and then go from there when it comes to identifying the intermolecular force type. Okay, so the first functional group we're going to look at are hydrocarbons. And if you look at all these hydrocarbons that we have here, we have examples of diesel and gasoline. All these are alkenes, alkanes, and alkynes. So some of them may have single bonds, some may have double bonds, and some may have triple bonds. But what they all have in common is they're made up of all carbons and hydrogens, hence the term hydrocarbon. These are all nonpolar. So these are going to have low melting points and low boiling points, all because of London dispersion forces. Some molecules have a super long hydrocarbon chain, and even though like in this example we have a polar end right here, this is the carboxylic acid end of a very long molecule, we could have properties of both polar and nonpolar substances. For instance, soap. Soap kind of works like this. So if we have some oil or some dirt, I'm going to make some green dirt right here. The nonpolar end of the soap molecule will wrap around the dirt and dissolve it, getting in between all its intermolecular forces, and then the polar end will be washed away by the water, removing the dirt. So soap is an example of one of these hydrocarbon chains that have both kinds of properties. So just because something is polar, it doesn't mean that it's going to always have totally polar properties. This long chain will definitely affect things. Okay, if you look here, these little OH groups that you see are hydroxyl groups. We call them hydroxyl. And they are the primary functional group in alcohols. All alcohols are going to be polar, thus having not only dipole-dipole, it's specifically hydrogen bonding because we have this H here directly attached to an N, O, or F. And so it's attached to the O. Therefore, that makes all of these alcohols polar molecules with hydrogen bonding. Next up, we're going to be looking at the carbonyl functional group. It's a C with a double bonded O to it. So right here we have a C. You'll learn about this way of writing stick diagrams when you get to organic chemistry. And this carbonyl group makes these molecules polar. Now, it's not hydrogen bonding because our H is not attached directly to the O, but it does create a dipole. So here's an aldehyde that has the C double bond O carbonyl group, and down at the bottom of the slide you can see that we have C double bond O's, but these are called ketones because the C double bond O, if you notice, is not terminal at the end. So here we have a ketone C double bond O, but here this is considered to be an aldehyde C double bond O because that is at the end of the chain, at the end of the molecule. You don't really need to know the difference at this point. You just need to know that the C double bond O makes a polar molecule, and therefore my intermolecular force is dipole-dipole. All right, next up we're going to talk about ethers. Ethers tend to be a little controversial because if you look, you see how we have an O right here? That O does make the molecule somewhat polar. Due to the orientation around that central atom. But these big fat CH groups, all those, that's a benzene ring. That benzene ring has a bunch of C's and H's in it. Benzene, and this one does as well. And those big fat groups are totally nonpolar. So for the most part, ethers have very low or very few intermolecular forces. There's not a lot of attraction because usually our nonpolar groups on the side of the oxygen give us symmetry, if you notice, to where the electrons are, making the overall molecule mostly nonpolar. So we're going to call this barely polar, and we're just going to stick with there being LDF forces. The LDF forces of these groups with all the polarizable electrons here are definitely the primary intermolecular force over the simple polarity from that central O. So I want you to just pretend that O is not there, and let's focus on these big nonpolar groups, and we're going to stick with these being LDFs for our purposes in AP Chem. All right, next we have here our carboxylic acids. The carboxylic acid group is a C double bond OOH. Sometimes it's written like Cu, and sometimes it's written C double bond OOH, like it is in this picture. Here is the C I'm talking about. But if you look at this group, these are highly, highly soluble in water because we've got hydrogen bonding going on here. And then we've got another very electronegative oxygen here, making this have a dipole moment here as well. So this is a very polar molecule, very polar, and we have intermolecular force of dipole-dipole here and hydrogen bonding on the OH of this group. All right, the next things that you see, these aren't specific functional groups. These are more types of molecules that you may see in AP problems that you have to comment on their characteristics. I don't want you to freak out about them. These are just pictures that you can interpret. So polymers, if you notice, are made up of all these carbon and hydrogen chains. And so based on what we've already talked about, we know that all those carbon and hydrogens are going to lead to good LDF forces. Very, very light, easy LDFs. But these molecules are big, so we're going to be super polarizable, so they're going to be pretty strong in the world of LDF forces. Proteins, you guys have studied in biology. You can see here that there's some areas that we can have hydrogen bonding occur. If you look, anywhere we see an H attached to an N, an O, or an F, those are sites of potential hydrogen bonding. There's also a little bit of dipole-dipole in here too. But for the most part, all our proteins, you know, and also think about our base pairs, all that stuff, back from bio days, those are all attracted to each other due to hydrogen bonding. And then this last one, these are glucose and fructose, and we make some disaccharides here. If we make sucrose is a mix of glucose and fructose. And you can see here that the actual functional group that we find on the edges of these are all sorts of hydrogen bonding. So we know that most of our carbohydrates and our sugars are soluble in water, and that makes sense because they're polar and they have hydrogen bonding. All right, what we have next are some scary looking structures that I actually pulled from all sorts of resources from AP. So like for the last 5 years, I went through all the practice exam this College Board gave out and any of the released exams that I could get my hands on. And I just pulled out some of the scariest looking structures that you might see. And I want you not to be scared of them. Remember, hashtag scary, not scary. This is not scary. You can do this. All right, so in this first picture, you can see we got a bunch of water molecules, and the question says in the diagram above, which of the labeled arrows identifies the hydrogen bonding in water? Remember, when we have water, we've got that dipole here, right? We have hydrogen bonds holding the O and the H together, but those are not the intermolecular forces. That's an intramolecular force. Remember that our dipole goes toward the oxygen, making this side partially negative and this side partially positive. We want to see an intermolecular force that exists between the oxygen of one water and the hydrogen of another water, and the only one that represents that is D. If you look at the others, they don't fit that bill. Like, for instance, let's see, A is wrong because that's an actual bond holding the molecule together. That is not an intermolecular force. B is an oxygen being attracted to an oxygen. Yeah, that doesn't happen. And neither does C, which is a hydrogen attracted to a hydrogen as an intermolecular force. So these are not even possible. This is a bond, not an intramolecular force, so the answer is D. Number 5 is also really simple. Which of the following is the strongest type of interaction that occurs between the atoms? Between the atoms, so we're looking for intermolecular, within the circled areas. So if you look, we have, that's the makings of a hydrogen bond, right? That's the makings of a hydrogen bond, and that is your answer. Your answer is C. These are just some pictures that I wanted you to look at. There was a question a few years back asking which of these substances, this was a polyurethane something or other, I can't remember, and this is PVC, like PVC pipes, and the question was which one of these was going to float in water and which one would sink. And so looking at the structure, if you think about things floating and sinking, we're thinking about density, right? So which one looks to you like it's going to be more dense? It's going to be this guy because of that chlorine. This N represents an unlimited number of possible repeats of that group in the parentheses throughout the chain. So that N is just multiple of those pieces. Well, chlorine definitely weighs more than CH3, so this one's going to and this is going to be the one then, the more dense one that actually will sink to the bottom. Here, I'm trying to remember what this question was about. I think this question, oh yeah, this was a question about which was soluble in water for this one. And if you look, due to the fact we have an electronegative Cl making this molecule more polar than this relationship, this one was more soluble in water. Here, which one of, for this problem here, you had to explain why this one has a higher boiling point than this one. And this was really easy because look at all that hydrogen bonding going on. So we're going to have a higher intermolecular force, a stronger intermolecular force, leading to a higher boiling point. Now, this is a polar molecule. We have a ton of dipole moment going that direction, but it's dipole-dipole. It's not hydrogen bonding like this one is. So this one's going to have a higher boiling point because of that. And on this question, if you notice, the main differences between these two molecules are, well, first off, sucrose, there's a lot of areas for hydrogen bonding, right? So it could be a question asking about which is more soluble in water, which is what I think the question was about, if I remember correctly. Sucrose has all sorts of hydrogen bonding sites, making it more soluble than lauric acid. Remember, lauric acid, even though it's got a polar end right here, remember we saw it earlier, and it's got that super long hydrocarbon chain. This end does not get along with water at all. This end does. So yeah, this might dissolve slightly, but because of all those different sites of potential hydrogen bonding in that sucrose, it is going to be more soluble in water. All right, the last two we're going to look at are another two multiple choice questions. This is a question about base pairs. Again, we have some biology on an AP exam, so I just don't want you to be scared. This is not something you can't handle. And they're talking about thymine and adenine and why they pair up. And it tells you that these two bases can form a connection between two strands of DNA via two hydrogen bonds. So that's key here. We're looking for the picture that represents two hydrogen bonds. And if you go through, all right, this is not a hydrogen bond because there's no H attached to that where I highlighted. Let's see here. Oh, not a hydrogen bond. Not a hydrogen bond. Oh, up here as well. That's not a hydrogen bond either. In C, even though this H to N right here is a hydrogen bond, it's not going to be attracted to another H, so that doesn't even make sense. Same thing here. We have a hydrogen bond here, but it's not attracted to an H. The one that makes the most sense is this one. We have a hydrogen bond here attracted to an O. The positive attracted to a minus, that makes sense. Here we have another hydrogen bond attracted to an N. So that makes sense. We have a positive and negative appropriately lined up. Again, partial positive and partial positive, not going to work. Here, no hydrogen bonding. Here, not hydrogen bonding. So the only possible answer to that would be D. And finally, the question here says, the figure above shows that in solid hydrogen fluoride, there are two different distances between the H and F atoms. Which of the following best account for the two different distances? Well, without even looking at the options, I see what's going on here. The first thing they're referring to when they're talking about this guy right here, that's an actual bond, right? That is a bond between two atoms. And when they're talking about this guy right here, that's an IMF. That's the IMF of hydrogen bonding. So this is a bond. That's an intermolecular force. They're going to be different in length because they're totally two different things. The only answer that works, if you look, is B, different in strength between covalent bonds and intermolecular forces, and that's the answer. Nothing, bond angles, got nothing to do with it. Different isotopes, what? We know nothing about neutrons. No, not that. And then uneven repulsion among bonding, non-bonding electron pairs. I don't even know what that means. No. So the answer has to be B. All right, that is it for this short little lecture. Hopefully the molecules won't seem as scary and foreboding any longer. Have a good day.